In today's episode, student, I want to talk about a physicist whose name many of you have only seen uh, through through his formula capital S is equal to K log of capital W. But without this physicist way of thinking, Planck's quantum step would be much harder uh, to understand. Now, this is the physicist I'm talking about is the story of Ludwig Boltzmann of entropy, probability, and a quiet, the whole foundation underneath our modern physics. See, in the textbook, uh, you uh, often see a sudden jump. You learn classical thermodynamics, and later on, when you study, almost abruptly, there is a Planck body radiation field, and then you are carried to quantum theory. See, but between these two, there is important conceptual bridge. The Boltzmann idea that entropy and probability belong together. If this bridge is missing, then perhaps the foundation of quantum theory would not be that solid. Anyway, so he Boltzmann taught us to think about order, disorder, and microscopic states in a new way. See, when Planck was trying to fit the radiation curve, he almost was forced to use this statistical language of Boltzmann. And then within that framework that we will see later in this lecture, he took a bold extra step of quantized energy. No, just quantized energy will not explain you the whole story. So the framework that helped Planck that we are going to see. So as I said in this lecture, we will highlight the Boltzmann framework, his core ideas, and quietly acknowledge some of his struggles in the later part of his life. So this is the quote from the man himself. See how beautiful this is, and it speaks for itself. A great quote from a great mind. Okay, in classical thermodynamics, Clausius, as we know, gave ds is equal to dq by t as a state function. It's very useful, very powerful. You know, it gives direction, but it is macroscopic, right? Uh, and you see, it is the foundation for reversible, irreversible things. But the basic question remained in the background. What is entropy really measuring? See, does it have any direct connection to the microscopic view, or there are certain foundational principles microscopic? That is what the question was. At that time, so see, the scene was leading physicists uh, did not treated atoms as something real. For them, it was still a fictional thing, maybe a mathematical picture for them, and not a really reality of the uh, universe. This is where Boltzmann central leap, we would say, comes in. He said, in effect, if we take atoms and molecules seriously, perhaps entropy can be linked directly to the number of microscopic arrangements. Microscopic, you see, we'll see what does mean here. So that's where his relation is. The capital S is equal to K log of capital W. Here, capital S is entropy. W is the number of microstates, the number of distinct arrangements, microscopic, possible. And that all correspond to the same macroscopic. See the connection between microstates and macro. And K is now what we call Boltzmann constant. Perhaps it is Planck who gave this name to the K. Simple way to think of it is a macro state. It is volume, pressure, right? Temperature. That's the micro scale we know of. And microstate is a complete specification of the positions and velocities of every single molecule. Let's put it that way. Now, the more microscopic possibilities there are, the larger W, right? And therefore higher entropy. Okay. So entropy becomes the measure of how many ways nature can arrange itself at a very bottom level, while still connecting to the same pressure, volume, and temperature. So Boltzmann added another now framework, which is very depthful, new view. So for a given system, now see this is where his great idea is. Uh, uh, any system can have many macro states in principle, which is possible. This is the basic idea. But they are not all equally likely. See this word equally likely, and some macrostates correspond to large number of uh, microstates than others. See, uh, so he is trying to give the connection now slowly between the macrostates and the microstates. He says there are many likely possibles, and out of these many likely macrostates, large number of microstates are possible for some of them, some of macrostates. See, so Boltzmann uh, trying to take us towards the equilibrium condition of microscopic states. Uh, So therefore, we can say in his picture, equilibrium is not. Uh, uh, See, macroscopically, we have no definition. It's there. But from Boltzmann, it's a spatial condition. What is that? It is simply the macro state with the largest number of microstates. See, this is the definition of the equilibrium, which nobody uh, of us realize uh, at a superficial level. Okay. So the one with the highest W, right? Microstate, which has highest W, will give the highest entropy, and highest entropy tends to equilibrium. And equilibrium is the macrostate that we observe without observing underneath uh, micro conditions. So therefore, the second law, which says that entropy tends to increase, can now be read in the language of probability. What is that? The system naturally evolves towards those macrostates uh, uh, that are more probable. Now, see, only those macrostates are possible uh, because for those for which the microstates are vast, right? Uh, Correct? See, matlab, highest microstate condition is what the nature sets in for the macros, like macrostate condition that are possible. So in other words, system move towards macrostate with the maximal microscopic freedom. Yeah, this is what. Now let's move to 1900, where Planck gave his famous papers, and he was struggling to settle down the problem of blackbody radiation. We will make another video for the mathematical details, but here we are just trying to give you the uh, and reflect upon the conditions and framework. Experimentally, this radiation spectrum was well known, and but classical theory predicted something uh, at that time known as ultraviolet catastrophe, which was absurd, which gave infinite energy as the frequency increased. So Planck needed the language in which he could ask, how is this energy distributed? He came up with the oscillator model, but then he said, okay, this in these oscillators, how can I distribute the energy, and how this distribution can connect me to the entropy, right? So for this, he had to turn to the Boltzmann statistical method to think the energy being divided into the small parts to count how many different ways this division can happen. See this, and then relate it to log of W. So, and he eventually came up, but he accepted that without Boltzmann's statistical ideas, the route to his law, famous law, would not have been possible, or would take much longer time. It was very hard. Boltzmann had given him the tools and the language. Mhm. So let us say with Boltzmann framework, which is S equal to K log W, probability and counting microstates. One of the radical thing along with this framework that Planck came with is quantization of energy, not continuous. He said, let's put in this framework E equal to h nu. And with this E equal to h nu and this framework, he could ask, given this discrete uh, quanta, how many ways now this energy can be distributed among the oscillators? These oscillators are nothing but molecules. What does this imply for energy and the average energy per oscillator? So this combination of ideas, on one side you have Boltzmann probabilities framework, and other side the hypothesis of energy quantization. This finally produced the actual experimental blackbody spectrum. In a sense, we can say Boltzmann provided the language and the conceptual tools, and Planck introduced the new uh, quanta, new rule of how energy behaves. All this feels quite natural to us today, but during his own lifetime, Boltzmann's lifetime, his ideas were not central, where we are far off from what was the culture, contemporary culture at that time. Some leading physicists openly doubted the reality of atoms. See now what is it. Others felt that bringing probability into the fundamental physics is somehow absurd. It is improper. It is simply philosophical. Even Planck himself was of this opinion. See, so people argued that entropy should stay purely macroscopic, and the talk of microstates and chances and all those is a speculation, and it is highly unnecessary. So Boltzmann had to spend years defending atomic theory and the statistical interpretation of deep value that he was seeking of the thermodynamics. There was intense debates, strong criticism, all those. And over a time, you can say it took a personal toll on Boltzmann. Well, it affected his health and mental state. Anyways, that is always the case. But here the point is to remember that pushing a new way of thinking in science has an you can say emotional cost for the person who carries it. And this was the case for Copernicus also, and for Galileo also. Galileo had to pay the high toll for setting the stream against the established giant Aristotle then. This is the point that I want to convey. There is a now striking irony at the same time as to what happened after Boltzmann. Within few years, Einstein gave the paper in 1905 about the Brownian motion, which gave the strong evidence, and people started to be convinced about the reality of atoms and molecules. Then Planck's and Einstein's quantum ideas quickly moved to the center of modern physics. The very concept Boltzmann had thought for years, atoms and molecules and real physical entities, S is equal to K log, probability as a fundamental tool in physics, became the part of the standard language of uh, 20th century physics, which we call modern physics today. On his grave in Vienna, you can see a simple inscription, capital S is equal to K log of W. Just this is a compact equation, but it symbolizes entire way of understanding the nature. Uh, so, and Einstein always believed uh, the deepest equation of nature are very simple. Today, when we study Planck's radiation law or Einstein's photon or modern statistical mechanics, we are quietly standing on the foundation that Boltzmann helped to build. He taught us to see macroscopic laws like pressure, temperature, entropy, volume as emerging from the countless underneath microscopic possibilities. Entropy, in his view, is a measure of how richly the nature can arrange itself behind the scenes. This small episode from is a tribute you can consider to the courage of bringing probability into the heart of physics, and to a scientist whose ideas quietly guided Planck towards the path of the quantum theory. So this is from Einstein on uh, Ludwig Boltzmann. See how Einstein respected this giant. And this is the inscription on his grave. Capital S is equal to K log of capital W. See if while listening to this story of entropy, probability, Planck's quantum step, if you have started to feel little meaningful somehow, then this tribute of Boltzmann, I would consider has reached its place. And thank you.